Hello. Today we're going to talk about topic 2.7, derivatives of cosine, sine, e to the x, and natural log. And we actually will talk about derivatives of logs of a different base. So log base, some constant other than e, okay? So at the very top, we're going to start with sine and cosine. Now what I did is I did put kind of the algebraic proof showing that the limit definition of derivatives still applies. The only problem is we've created, or they've given you, some shortcuts, if you will. You don't have to show the proof of sine every time you take the derivative of it. Instead, we can just say here, we know the derivative of sine is going to be cosine, okay? Or the derivative of cosine is going to be a negative sine, all right? Now, this is a very cool exploration graphically. So if you have the time, if you want to pull up the sine function or cosine function on Desmos and start to take a look at where positive slopes and negative slopes are, where it's zero slopes, you will start to see how they the derivative of one makes the other, okay? So that is a very interesting exploration. For this topic, though, we're just going to look at it in an algebraic sense, and we're going to use these two definitions, okay, or derivatives. So if you take a look, for example 1, find the derivative of each of the following, right? So now it's denoted y, so we're going to say, okay, well, y prime. Now 2 is a constant multiplier, so we don't need to take the derivative of that. However, the function of x here is sine, so the derivative of sine is going to be cosine, right? So I can say y prime is just going to be 2 cosine of x. And this is my derivative, or the expression to find the slope of my tangent lines, or the instantaneous rate of change. Okay, so let's take a look at some other examples. Let's look at B. So y, now another notation, instead of y prime, you can use dy dx, right? So if I take the derivative of this. Now, I want to show you how I would rewrite this, just to show you kind of like it makes a little bit more sense algebraically. I'm going to write this as a 1/2 times sine of x, right? If you divide by 2, it's the same thing as multiplying by half. And when you have that constant multiplier, that 1/2 does not need to be part of the derivative. Instead, I can just say 1/2 and then the derivative of sine is cosine. And I can say that the derivative then is cosine of x all over 2. Okay? And I get my answer. All right, now you have to be very careful with quotients. We're going to get into a later topic how we approach those quotients a little differently if we have variables on the top and the bottom. But in this case, we are just dividing by a constant. So I wrote it as a constant multiplier and took the derivative with what we know. Okay. Feel free to pause. Try to do part C. I'm going to do it here in a second. So I'm going to call it y prime. You can use dy dx. Derivative of the x is just 1. Derivative of cosine, well, we know from above, is a negative sine of x, right? So if you look up here, cosine is a negative sine. So I would write my derivative as a 1 minus sine of x. And this would be the derivative. Okay? So let's go to the next one, e to the x. All right? Now, e to the x is special. It is one of only 2 functions where the derivative is itself, okay? So if you take the derivative of e to the x, you still get e to the x, okay? Now, the only other function that does that is 0, right? The derivative of 0, constant, is still 0. But this is the only derivative where you will get itself, and it only works for e as well. So if you had a different constant other than e, then this wouldn't apply. So if you have, for example 2, part A, if I take the derivative of this, well, the 5 we don't take the derivative of. That's a constant multiplier. And the derivative of e to the x is still e to the x. So my derivative for this function, believe it or not, is still 5e to the x. Okay, now we do have to worry when we have more terms. So if you take a look at part B, if I were to say, okay, dy dx. Now, the derivative of e to the x is still e to the x, but the derivative of a negative 4x, we're going to use power rule there. So I'm going to say minus 4, it'd be x to the 0. So it would just be e to the x minus 4. Okay. Part C, I'm going to use a y prime just to keep you up with, variety of notation here. Make sure you're aware of all. So derivative of 7 e to the x is still 7 e to the x. The 7 is a constant multiplier. The derivative of e to the x is still e to the x. But now, if you remember from above, I don't know if you've forgotten them already, but the derivative of cosine of x is a negative sine of x. So I have y prime equals a 7 e to the x minus sine of x. And this is my derivative. Okay. Now, next is a natural log. Okay. Now, there is a catch with natural log that I want you to be aware of. So, if we have the ln of x, okay, I don't know if you guys know the graph of natural log of x, but it looks a little something like this. All right. Now, the derivative of natural log of x is 1 over x, which looks a little something like this. Now, just to be clear here, you can't have a derivative where the original function doesn't exist. So if you take a look, I'm going to kind of highlight here, or I'm going to bold it. This section of my graph is only when x is greater than 0. So the only section of the derivative that I want to do is in the same x values. This part of my graph doesn't make any sense. I can't have outputs for the derivative if my graph was never there to begin with. Okay, so there's a little disclaimer that I want to put on this line. The derivative of natural log of x is 1 over x as long as x is greater than 0. Okay, so if I were to take the derivative of this function, all right, dy dx is going to be, well, the derivative of 3 natural log of x. The 3 is a constant multiplier. The derivative of ln is 1 over x minus derivative of 2e to the x we just did is still going to be 2e to the x, because remember, e to the x stays the same, minus 1/2 derivative of cosine is now going to be a negative sine of x. And we need to put a disclaimer here. This derivative only applies when x is greater than 0. Why? Because we took the derivative of natural log. When you take the derivative of that natural log, it's now going to give you a restriction on your derivative. Okay, so if I do this, I now have a 3 over x minus a 2e to the x plus a 1/2 sine of x. When x is greater than 0, right? But this is my derivative. Okay. So what happens if it's not if it's not natural log, right? If it's a log of a different base. So we have this idea. Now, I want to show you just kind of the quick way to do this. If I have y equals natural log of x, that's the same thing as saying log base e of x. So if you were to take the derivative of this, I'm going to use the same formula. Now watch what I do here. Off to the side, I'm going to say a 1 over the natural log of the base times the argument of what's inside your log. Now, I don't know if you guys are familiar, but the natural log of e is just 1, and I get 1 over x, which is what we had above. Okay, so ultimately they're doing the same formulas, but for natural logs, the log is, the denominator is going to have an ln of e, which is just 1, it won't apply. But here, we're going to get this extra little piece. We're going to get this 1 over ln of b. Now, I'm going to kind of show you the proof for this. I want to show you how this works. So if you were to take the derivative, right, of, I don't know if you guys remember change of base, it would be the natural log of x over the ln of b. I can rewrite this to be 1 over the ln of b, because that's all a constant, times the natural log of x. So 1 over natural log of b, that's all a number. That's going to be a constant value. Remember, b is going to be a discrete value. So if I take the derivative, I don't need to take the derivative of a constant multiplier, but the derivative, I'm going to say the derivative is going to be then the derivative of ln x is 1 over x, which gives me a 1 over x times the natural log of b. And this is where we're at, okay? So I want you to be aware, I still have a 1 over x if it's not a natural log, but in the denominator, you're going to get a natural log of the base with it, okay? Now, let's take a look at, I wanna make a connection between the derivatives that we did in topic 2.2 using limits and what we're doing now. Okay, so that's very important. So I want you to take a look. These were the definitions for derivatives. Oops, sorry about that, guys. If you take a look, this is what we use the most. And AP also likes to use this one from time to time. Okay. Now, if you take a look at this, I want you to say this statement is synonymous to saying the derivative of sine of x at x equals pi over 3. I want you to see, okay, I'm going to draw a little arrow here. I want you to see the relationship between how this is set up and our definition for the derivative. Now, I do not want to simplify that limit statement. So what I am going to do is I'm going to rewrite it, and I'm going to figure out what the function is and where they want me to evaluate that derivative at. If you can look at that expression, that limit expression, and recognize it as a derivative, then you can do this problem very, very quickly. If you don't recognize it as a derivative, well, that's why I put this up here. You would have to prove that sign, that limit with sine of x plus h, and we don't want to have to do that. So we want to look for when these limit statements are derivatives, and not all are, but this one is set up that way. Okay, so what I want to do is the derivative of sine is cosine, and then I want to evaluate that at pi over 3, because again, that's what my x value was. My x value was pi over 3, all right? And what is the cosine of pi over 3? Well, pi over 3 is the 60-degree angle on your unit circle. So we will get the value of 1/2. And that is my answer, okay? That is incredibly simpler than trying to expand that limit, trying to reduce it, and then substituting in a pi over 3, okay? Let's take a look at this next one. Now I want to show you here that this one actually uses our second definition for a limit, all right? So limit of f of x minus f of c all over x minus c. This is f of x minus f of e all over x minus e, okay, if you look at that notation. Now, this is just saying, and these are hard to recognize, so if you don't see them right away, it's okay, but this problem is ultimately just saying, take the derivative of the natural log of x at x equal e, okay? Now, the derivative of natural log of x is 1 over x, okay, as x is greater than 0, but we don't have to worry about that because e is bigger than 0. So if I plug e in, I get a 1 over e. So if you get a weird limit statement that you don't know how to reduce, odds are that it's probably a derivative statement, and you need to start trying to analyze what that function is, right? So if you get a limit statement that you don't know how to reduce to get an answer for, start trying to identify, is it a derivative? And is it a derivative of what? Right? So same thing here. You know, I really don't want to evaluate this limit statement. So I'm going to start to look at it a little closer, and I'm going to figure out, okay, is this a derivative expression? And if it is, what am I taking the derivative of? And if you can do that, you can make those limit problems significantly easier. Now, I do want you to know that that this topic does also include tangent lines, all the stuff that we've done on the previous notes, right? So I can give you a function now with sine, cosine, e to the x, natural log of x, and I can still ask you for the equation of the tangent line. I can still ask you to find the slope at a point, you know, and the instantaneous rate of change. So I just want you to be aware of that, that you can still find the derivatives or the same information just with a broader spectrum of functions now. Thank you.